Well, hi everyone. My name is Theo. I'm a machine learning engineer at ai-coustics, a company based in Berlin. Flew in today to Paris. Very happy that there's sun here because in Berlin it's tough. Luckily, I mean, we had sun like yesterday, a couple of days ago, but I was just praying that we had sun here as well because Jesus. Very happy to be here and very interesting demos and talks. So. I'm here to talk about our latest model. It's called Quail Voice Focus. And it's a model that operates with audio, and it's for speaker isolation. So let me give you a bit more context regarding this. OK, so I'm just going to play an audio right now of a phone conversation between a human and a voice agent. And the audio will just speak by itself. Let's see.
Yes, definitely. I remember thinking about getting a solar for my home, so I'm definitely very much interested. In it, yeah.
That's great to hear. Thank you for confirming. To make sure we can provide the best advice and solutions for you, I'll just ask a few questions.
Yes, I'm listening. Michelle, are you good? Did someone kill you? I hope you're there.
Well, luckily, Michelle was a voice agent, so she didn't die. But you probably get the gist. So what happened here is the voice agent was interrupted by background speech. And this can be quite frustrating sometimes when you're like in very loud environments and you're expected to have a conversation with a voice agent, and the voice agent just thinks that you're speaking, but you're not. So this is basically it's not a flaw on the agent per se. Like this agent works with speech-to-text models. I mean, Benjamin already talked about this. Pioneered as well. And the thing is, speech-to-text models, they usually are made for basically capturing all the intelligible audio. And that's the design of the solution. That's not an issue. But the issue is that sometimes when you speak to voice agents, you don't want to have all this background audio. You want to isolate the main speaker, and you want to basically all what's far field distractions, you want to remove it. So people around you, TVs, radio, anything that could like distract the conversation, could steer it somewhere else, you just want to get rid of it. So you want it effectively like a filter that can do that. And this is why we built this model called Voice Focus. And I'm going to give you a live demo right now. So, go back. Right, so this is on Hugging Face right now. It's public. Anyone can use it. What I'm going to do, hopefully it works. I haven't tested here with a microphone, but we'll see what happens. Right, so what I'm going to do, basically, I'm going to start speaking, and we're going to have a live transcription from, well, here we're using a Zoniax as our speech-to-text provider. I'm going to start just talking. OK, so I'm being transcribed right now, live, by two, well, it's the same speech-to-text provider. But on one side, we have Quail pre-processing this audio and filtering out, ideally, the background speech, and on the other side, we have the raw transcript. So left side, enhanced, right side, raw. I'm going to play a video of myself speaking to try to enact a background speaker relatively close to the microphone. And, well, let's see what happens. OK, see if this works. OK. OK. So here at ai-coustics, we built. I don't know if you can hear it. This is the max volume from my phone. The goal is simple: But basically what's happening is I'm being transcribed by the raw transcript, and with the enhanced model, this is not happening. And that's what we tried to do here. We tried to basically get rid of background speakers and just keep the foreground speaker. So I'm going to stop the demo right now and explain a little bit how we did this. All right, back to the presentation. Okay. Well, I'm not gonna talk too much about how we train our model. This could be a bit overwhelming, but basically what happens is how we train our model was we kept in mind two things. So first of all, we wanted to make sure that we optimized for speech-to-text performance, so not human perception. So we didn't want the audio to sound pristine. We just wanted the audio to be transcribed correctly. So that was number one. And number two, we wanted to mimic real-world scenarios so that the model could pick up on cues that actually happen in the real world. So it could learn in real time what's happening and who's the main speaker and who's not. So usually you have, when you train a model, well, for this kind of scenario, well, you start with a primary speaker and noise, and then you can combine them, and then you teach a model to just ignore the noise. That's a denoiser, and people have gone very good at it. But this is an oversimplification of the real problem here, at least for our use case. So what we did was add more speakers, secondary speech, and media devices like TVs or radios, and we tried to also, just to get like a more challenging situation here. And then we stitched everything together with something we called room simulation. So we basically put like the main speaker virtually in a room, close to a microphone, and then added speakers in the background at different distances, other distractions as well, like noise. And we just computed based on the reverberation of all these other sources, how the model, just to teach the model, these people are too far away, ignore them. Then we added more things that I'm not going to go over right now because it could be a bit overwhelming. But we have a whole other section of augmentations for our data pipeline just to mimic the real world as close as possible. But I'm going to skip over this. If you have any questions later, I'm happy to answer them. Then basically once we have our trained model, how can we evaluate it? And this was also a tricky part because the previous part we could do synthetically, but evaluating your model, you want to make sure that it does well in real life. Okay, this image was made with AI by Fabian, one of the co-founders of ai-coustics. And you can tell it's synthetic because the guy's hand is peeking out of the glass, which cannot really happen in real life. And this is kind of what we were seeing with the data sets that we found, the evaluation data sets that we found on the internet. They were okay, but they were just not what we see in real life. So in order to, well, let me give you an example. So for example, on Hugging Face, you have the speech recognition leaderboard. And here you have a bunch of speech-to-text models that are incredible. You have Parakeet, like it was mentioned before, and many others. And these models do very well at transcribing speech. On these open source data sets, they have very low word error rates, which is amazing. But the issue is that this is not depicting really what you see in the real world. These open source data sets, they are not they're not for a use case. They're very good for scenarios like the one that I was mentioning at the beginning, when you have maybe a meeting and you want to transcribe everyone. But if you want to ignore background speech, this is not realistic. Another example is, for example, Pipecat also released a benchmark, STT benchmark data, where they tested a bunch of commercial STTs on their data set, and they all did incredibly well, and that's amazing. But if we listen to some of these samples, okay, we can't hear. Let me see. All right. Well, I guess you're gonna have to trust me on this one. But basically, these samples they're just very clean. They might have noise and so far and so forth, but they're not representative of what we're trying to do here. So I'm gonna get back to the presentation. Yeah. So that's why we also tried to create a new evaluation data set to try to mimic the real world. This is obviously an exaggeration of what's happening in the real world, but like I think, well, you get the gist. We're just trying to mimic noisy and I guess real life scenarios. So what we did, we basically created a semi-synthetic data set. So we used pre-recorded clean speech, and then we passed it through. I mean, you see my cursor here. This is an artificial mouth. It's basically a speaker that mimics human speech. And so while this artificial mouth was speaking, basically, we had also some background speakers. You can see also up here, we had some other speakers in the background that were like also playing background speech and noises and other things, basically the stuff that you don't want in your final audio. And all this was being recorded with a computer and a phone. And then all this audio then was sent to different messaging apps just to get also compression and just to try to mimic the real life cycle of audio. This was, well, I also want to say this was a very fun project to work on. Yeah, although it was tedious and time consuming, it really gave us a data set that we felt like we were like pretty comfortable with evaluating a model. And we called it Donchorus, and we made it open source. So it's also on Hugging Face. And I wanted to show you how it sounds, but apparently the audio is not working. So I mean, I'll try. Maybe it's fixed now. Let's see. OK, it's not. But basically, this data set contains 450 samples of clean main speaker ground truth. And then we have a mix here on the side, which is like speech also with background noise and with like artifacts from compression and noise and stuff. And then we also have human verified transcripts that come with the data set so that you can also see if it actually transcribes well. Should I try again?
Not sure.
Okay. OK. Then, well, OK. You can just look it up on Hugging Face. It's open source. Let me go back to presentation real quick. OK, so then we used, yeah, I have to talk about plots, of course. Then we used this model to evaluate, so this data set to evaluate how the different speech-to-text providers work with and without our model, Quail Focus. And we saw some surprising things. So first of all, well, here this plot, we have here the word error rate, which indicates how well transcriptions are going. Higher the word error rate, worse. And we have the gray bar, which is without the model, and blue bar with the model for different speech-to-text providers. And although we can see that with the model, everything works a little better, it's interesting seeing how different it works across the different speech-to-text providers. For some of them, we only improved 10%. For others, almost 50%. But another important thing that we found was we split the word error rate into insertions, deletions, and substitutions. And we saw that the insertions was the main force that drove the word error rate for all these speech-to-text providers. And with the model, we were able to reduce that because we were able to get rid of a bunch of this background speech. But to be fully transparent, also at the cost of more deletions. And this is a good segue for my next slide. OK, so word error rate, insertions, deletions, and substitutions. Basically, yeah, it's always like a balance. And when we saw that, we decided to test a couple things. So we wanted to see how well, we wanted to see basically if we could be the best in terms of insertions and deletions and substitutions. So we basically tried experimenting with a parameter that we call enhancement level that basically is able to control the aggressiveness of the enhancement per se. And we tested it on 2 different commercial STT providers. And we saw that the behavior is similar. The less amount of enhancement, the more insertions we have, the more amount of enhancement, the least insertions we have. Insertions are in blue, by the way, but also deletions kind of go up as we enhance more. So we just decided to expose this parameter for users to be able to decide how much enhancement they want to use, because, for example, for DeepGram, this trade-off kind of like happens earlier in the enhancement level, but for Zoniox, it happens later. So ultimately, we just wanted to let the user decide, because everyone has a different audio stack. Every speech-to-text model works differently, so we just said we can't have a one-size-fits-all. Let's let people decide how much they want to enhance their audio. Yeah, and with that being said, you can use this model. It's available on 2 platforms, LiveKit and PipeCat. They're both platforms for real-time AI pipelines. And in case you have a custom stack, you can also integrate it with a SDK. It's also very simple. You don't have to talk to any salesman or fill up any forms. You just sign up in the platform, put your email, and then you can just create an SDK key and just read the docs, and just, in 10 minutes, you can have it working. So thank you very much for listening, and any questions you might have, I'm here to answer.
Thank you, Theo. So who has one question? Yeah.
Thank you. Thank you for the presentation. It was very interesting. So my question is, so basically I have 2 questions. Yeah. So the first one is, did you try to to collect more data in a different environment, like in different rooms or with different maybe neighborhoods, behavior, stuff like that? Because this is one of big issue. And the second one is, when you let's say delete the background noise, did you intervene from basically on audio side, or in both on let's say on text side? I mean, did you play with both, or we just sound levels and stuff like that?
Okay, so for the first question, thank you for the question, by the way. For the first one, for the training, we had to create a lot of data, and to create all this synthetic data, we used many different virtual rooms. So we captured different room impulse responses to have different reverbs and different conditions. For our evaluation data set, it was all done in the same place with different speakers, but yeah, it was in the same room. So we are working on expanding this to have it happen in more places. But yeah, so far it's very hard to obtain real world data that is good enough to mess up the transcripts, but it's also not so hard that it's impossible to transcribe them. So it was pretty hard to get this data set. So we knew that room worked very well because everything was well under control. But we're trying to expand it. But for the training, many different rooms, virtual though. And for the second question, we only work with audio. So our model only touches audio. Of course, to see if it works well, we're constantly looking at how well it does with transcription as well across all these STT providers. So, but yeah, we only touch audio.
Yes. And then it's going to be the last question.
Thanks for the presentation.
Closer to the mic.
Yeah. Thanks for the presentation. I have 2 questions. One is regarding your data set creation. I mean, your setup looks pretty standard. I mean, have you tried simulating it instead of, once you measure the impulse response of your speaker positions, everything, instead of changing the rooms or instead of changing the speakers, you can simulate everything, right? Have you tried simulating? It's just purely live recorded data.
We tried simulating it, and we never got results that sounded convincing. That's why we went for like a real recording, because ultimately there is like compression from, I guess everything was being recorded onto like regular devices, and we also like wanted to make sure that, yeah, like in our case, when we tried doing it artificially, there was always, like, you could always tell that there was something wrong. And once you put everything together in the real life and you compress it using like different compression, like codecs and stuff, you get like an actual feel that everything is real and comes together. And that's something that we've never been able to do synthetically, but it worked well enough, I guess, to train our model.
Cool. Yeah. All right. And the graphs that you have shown, like, what are the minimum number of microphones do you need? Like, were they all based on single mic data, or do you need like multiple microphones
For the graphs?
for the speech enhancement to work optimally?
You mean this one?
Yeah.
I mean, all of this was done with one microphone. Yeah. What do you mean using more microphones? Sorry. Okay. Okay. All right. Well, thank you for the question. Perfect. All right.
Yeah.
We're good.
Thank you
Okay.
very much. Yeah.